Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 11 of Arrow 4080. Today we're going to be extending our study of beams, the hand finite element of beams, to see how we might account for distributed loading on the beam. Let's see how that works. So let's say we have a beam. Let's say it's a fixed beam and we have a distributed load. Now, if we look at our handbook, our Arrow 3271 handbook, or our Arrow 3261 handbook, in the appendix, we have a number of cases of the hand solution of different kinds of beams. And within those, you'll find a fixed beam with a distributed load set of solutions. Now, mostly we use that to look at what the deflections are in that beam, but we also see what the shear, what the reactions are, and what the moments are for that beam. And if you look at those, you find out that a beam like this, a fixed beam with a distributed load, has a reaction equal to WL over 2 on each end, and it has a reacting moment of WL squared over 12. So if we have a beam that's continuous, since this loading causes those reactions on a beam that distributes moment and shear into the support, we can actually simulate the effect of that distributed load by applying those loads on the beam element. Now, you'll notice here, what we're seeing here is if we have a distributed load, the reactions are going to be opposing the load, and the moment is going to be opposing the load. It's the reactions. If we want to simulate that applied loading, what we're going to instead do is apply a applied load similar to those reactions, but to simulate the applied shear at each end of the beam. And we'll apply a moment instead of the reacting moment. We'll apply the equivalent applied moment. So it'll be the opposite of these directions shown here. Okay, you with me? We're going to see how that works in a second. All right, since those resultants completely describe the effects of that loading, we can use those, the opposite of those reactions, to simulate the load. So for example, if we have a beam like this, we've got 1, 2, 3, 4 nodes and a distributed load in the middle. We note that at the two ends of that beam, we would then apply an applied shear at each end, WL over 2, and an applied moment. You'll notice it's going in the same direction as equivalent moment at those two endpoint nodes. That will simulate the effect of that distributed load on the beam at that node. Okay? So now what we're going to do here is, notice, if we only wanted to look at the beam with the element shown here with 4 nodes, then that's all we would need to do. But if we have a beam like this, we're probably going to want to know what happens between the supports. We're going to want to know the deflection there. If we want to know the deflection there at the center of the beam, we're going to need another element. So what we're going to do is actually add one more element, put one more node right in the middle of that beam, right in the middle of the 2-3 span, so that we can actually retrieve a deflection there and whatever moment occurs in the beam there, right? Right now we don't have the internal loads at the center of that span unless we put a node there. So we'll go ahead and put a node there and apply our load. If we do that, we now have 1, 2, 3, 4 elements. You'll see you have 1, 2, 3, 4. That was the original nodes. We add another node at the center. We don't need this node, except that's the only way we will be able to retrieve information at the center. Then we apply our loading. The only applied load to this beam was the distributed load, so we're only going to put in the simulating load. So at node 2, we're going to have the shear and the moment that simulates the effect of the distributed loading. At node 3, we're going to have the shear and the moment associated with distributed loading. And then at node 5, you'll notice from the left, from the beam element from 2 to 3, we're going to have applied shear and a moment. And from the 5-3 span, we're going to have a shear and a moment. So the total shear will be WL over 2 plus WL over 2. And the applied moment there will be 0. Do you see that? Because those two are going to cancel each other. Okay. What we're going to do now, what we see then, is we have normally our force vector, F, capital F, has all the external loads on the beam. And we will retrieve out of so parts of that F has the external loads and parts of that has the reactions. Now in this case, the only external load is one that we couldn't apply directly between the span. So the way we accounted for it was by converting it to an applied load. And these loads at the nodes are now those converted loads. So actually, this WL over 2, this WL squared over 12, and the rest of the same are now external loads. So we're going to make a new vector, but we're actually going to call it FO, not just F, because FO has those simulated forces. It's not all of the applied forces, it's only the simulated forces. Okay? You got that? So FO is going to be a vector, a force vector, an applied force vector that only includes the simulated forces. And this is simulating that running load. Okay. With that said, I think we're ready to go and summarize our little method here. Here's our little beam. We have the forces. Once we have these forces that simulate the loading, we then can determine our deflections in the beam. We're going to calculate our local stiffness matrix as we did before. We're going to construct our global stiffness matrix as we did before. We're going to reduce our global stiffness matrix by imposing our boundary conditions as we have been doing. We're going to then use our applied external forces, which include FO, to solve for the system of equations. That means if we only have that distributed load, then FO will just be that distributed loading simulation. If we have multiple applied loads, including a distributed load, then we will have a vector which includes FO. Right now, let's just focus on just that simulated load, FO. So we're going to use FO, and we're going to reduce our matrix to solve for the displacements. We then, as we did before, we will use those global displacements to calculate our constraint forces, right, by solving the system of equations. Actually, we solved the system of equations here to get the deflections, and now we can just multiply the global stiffness matrix by those displacements to get the total force. Now we're going to call these forces, instead of that being the resultant force that we get normally, we're going to call this F effective, and we're using a little g to note that it's in global coordinates, okay? So we're going to call that the effective now. Usually we were done at that point. We had those external reactions and the applied loads. But remember, this vector, FGF effective, includes both the constraining forces and the applied forces and our simulated forces. So what we're going to need to do now is subtract the simulated forces, FO, from FG effective to get our FG, our constraint forces and applied forces other than that, those simulated loads. Okay, this will give us our external reactions and nodal forces. Okay, all right. Now, since these exclude the nodal forces due to the idealization, right, we're going to now modify our next part of the procedure by solving for our element forces. We're going to use the global displacements at each node times the global element stiffness matrix. But now, since those forces include those simulated forces, we're going to have to remove the simulated forces from that, because those are external applied loads, to get our actual internal loads in the beam. Okay? Now, once again, this little vector to the furthest right with a shear and a moment, these are those simulated forces. They're the parts of FO that apply to this particular element. Okay? That's how we're going to tweak our procedure. All right. Now, That was for a distributed load on a beam. Remember, we're just talking any beam element. We use the fixed case because a continuous beam, any beam that's continuous that's attached to other structure, has the potential to transmit that moment. So regardless of how the beam is constrained, if we have a beam element used anywhere in our model, we're going to use that simulation we just developed for a distributed load. In the same way, if we have a beam element with any of these other applied loadings, now we're just looking at the loading, we're not looking at the end constraints. We're going to imagine that this is a continuous beam element, therefore we're going to use the fixed case, simple case like what we see in the appendix of our 3261, 3271 handbook to develop our loading function. So if we take a look at that, we see, okay, if we have a point load at the middle of a beam, we can simulate that by at the left end of the beam we apply the shear and moment we see there, and at the right end we're going to apply the shear and moment we see there, and so on. So we're going to see this table gives us the shear and moment at both ends of the beam that we can apply in order to simulate that loading. You see that? Being careful with the sign convention and with the sign. Now you'll want to notice here that your text doesn't have case 5b. I provided that for you, so you can go ahead and include case 5b in your beam, in your text. Write that in or paste this into your textbook so that you can see how to simulate that other one as well. Okay? So this gives us our shear and moment to apply at each node. Now if we get case 1, we're actually not going to use this approach. What we can do is just break up our beam in one more spot, put a node in the middle, and we can apply that external force. And same thing with case 9. If we have an applied moment, all we need to do is break up another node there and apply that moment directly. But what this does do is provide a method to get the effects of that loading without having that loading. See how that works? Okay. And for some things like distributed loads, that's the only way we can do it. All right. With that said, we can summarize our method for distributed loads by as follows. We're going to model our system. As always, we're going to develop the local stiffness matrix of each element. As always, we're going to transform those local stiffness matrices into global stiffness matrices. Then we're going to assemble our global stiffness matrix. As always, we're going to determine FO, which just is the simulated parts of loading. So anytime we have a beam element and we don't have a node, we don't have a way to put the external forces at the nodes, if we need to apply a load between the nodes, like with a distributed force or a gradient force or something like that, then we're going to go and simulate that part of the loading that's not at a node and come up with FO that simulates that load. Then we're going to use our boundary conditions to reduce the stiffness matrix as always, right? And then we're going to calculate our external forces with the displacement. We're going to use those, we're going to use the reduced forces to calculate our displacements. Now, once we have those displacements, we can use those global displacements to go and recalculate any forces that we're missing, but those are the effective forces, which we now need to modify by subtracting FO. We then will remap FO to each and every element, and we can now use the global displacements times the global element stiffness matrix to calculate the global element forces once we've subtracted out whichever simulated forces, whichever parts of FO were at the two end nodes of that element. Okay? All right. And since in this particular case our beam element is aligned with our global stiffness matrix, we don't have any transformations to do later. We'll need to transform those matrices if we have an element that's not in line with the global stiffness matrix. Okay? We then calculate our element stresses. Okay? Now we could use this approach to simulate external loads that don't apply at the nodes. We saw a few of those cases in our table a moment ago, but we're not going to do that in this class. Anytime we have an external load, we're going to actually we're going to break up another element and calculate that, okay? We'll only use this procedure in our class to simulate distributed loads, gradient loads, and things that can't be idealized by just plugging in another node. Got that? All right. Here's a little example. Let's say I have a cantilever beam with a distributed load. You'll notice there are no external loads except for that distributed load. In order to account for that, since we mostly are looking for information at the right end and at the left end, we can actually use a single beam element to solve for this. However, we're going to need to apply our distributed load, since that is applying to parts of the beam that are not at the nodes. Okay, so we're going to use our new procedure. So here's what we're going to do. This is an echo of our two nodes for our beam, and this is an echo of our beam properties. We now can go and calculate the FO for that. As you'll notice, this distributed load, we're pretending that is fixed when we distribute when we come up with our effective loads. You'll notice that loading there is going to have a downward WL/2 shear at both ends, and it will have a moment WL squared over 12. You'll notice one of them, using right-hand rule, is negative moment, and at the right end is a positive moment. That gives us this FO for our beam at nodes 1 and 2. You see that? Okay. Now we can go and calculate using our local stiffness matrix, convert that to a global stiffness matrix for the element, and then convert that to a global stiffness matrix for the whole structure, which in this case is just that same stiffness matrix. We then can reduce our system. We see that node 1 is constrained for both vertical deflections and rotations. So we can eliminate those parts of the global stiffness matrix. Bang, pop. That gives us our reduced global stiffness matrix. We can multiply that by our forces, which include FO. In this case, FO is the only part of those forces, and that gives us our deflections. We then take those deflections and we multiply our kg by those deflections to get our effective forces. We then subtract our FO from those effective forces to get our constraining forces. See how that changed it? Okay. And then we can use the forces at each end, those displacements at each end, and multiplied by our global element stiffness matrix to get our forces, our internal force of the element. But we have to subtract out the applied forces at the nodes as well. So at node 1, we have to subtract out the F1O that we applied and the M1O that we applied, and the same thing at node 2. That gives us our element forces, which we find are these. And that makes sense because we see at the left end we have a reaction shear and moment. At the right end it's free, there's nothing there. See how that works? Let's take a look at another example. This example looks identical to the last one, but now we're going to see the effects of having external loads and those simulated loads. So we have this distributed load, which we're going to have to simulate, and we have this applied load, which we already know how to handle. So it's the combination we're going to look at this time. So once again, we echo our nodes and our beam properties, and we're going to use this simulation for the distributed load. Okay? See that? We've got this simulation for the distributed load at node 1 and node 2. We then are going to take our local stiffness matrix, which happens to be our global stiffness matrix, and we can remove our constraints. We then can calculate our displacements using all of the applied forces, which are the F vector, which just is P, has P in it, and our FO vector, which we just determined, okay? Because that's the total set of applied forces. The ones that simulate the distributed load and the ones that are just applied at nodes. That gives us our displacements. We then use those displacements to calculate the effective forces. We then subtract the FO from the effective forces. We're not subtracting that P part of the force, we're subtracting only the FO parts. We then use the deflections, the global deflections, and subtract out, use that against our stiffness matrix, subtracting out our applied loads, our simulated loads, to get the element forces and moments. Does that make sense? Okay. Now here's an example of a gradient load. Now this one has a gradient load, and if we wanted to just do this with one element, we could do this with one element. But in that case, we wouldn't be getting anything. We wouldn't have any way of calculating anything because we've got nothing moving. We'd just be going from a fixity to a fixity. So if we want to see the effects of this loading, say at the middle of the beam, we would have to break up the beam at that point. So let's say we model this with a node there at the middle. And if we did that, then we would have 3 nodes, and these would be our properties for the 2 elements. We now, looking at this, we say, okay, how do we simulate this? Okay, we're going to break it into pieces. We need FO. We're going to have to break it into 3 pieces. From 1 to the middle is 1 piece, denoted 1, and then from the middle to the other end. Now, if you think back to what we learned in 3271 about singularity functions and how we broke up those loadings, we're going to break this up in the same way. We can build up that loading from the middle of the beam to the right end by looking at it as 2 pieces. One of them is a uniform distributed load and one is a gradient distributed load. So from the left end to the middle, we've got a single gradient that we need to simulate. From the middle to the right end, we've got a uniform load that's simulated and a gradient load that's simulated. And that will provide all of the simulation that we need. So once again, these are the 2 cases we're going to need. These are the left end and right end values. So we can go and simulate our loading 1, our loading 2, and our loading 3. You'll notice loading 1 is for that first part of the beam element, and the loading 2 and 3 are going to have to be added together for the right beam element. Okay, that gives us this FO. We're going to have a force and a moment at 1. We're going to have a force and a moment at 2, and we're going to have a force and a moment at 3. Notice at 2 and 3, the FO is the summation of the 2 cases that simulate that. Now that we've said that, we're ready to move forward. That's our local stiffness matrix of each element, and that happens to be the global stiffness matrix. We can assemble our global matrix and then eliminate at both ends. We are constrained from having a deflection or a rotation. We can apply our portion of the applied loading, F plus FO. In this case, it's all just FO, right? The reduced part of that to calculate our deflections. We use the deflections to calculate the F effective. We use the F effective, subtract out our FO to get the constraining forces, and then we can use the deflections at each node, subtracting out the simulated loads of each element to calculate the elemental forces. Okay, you're going to practice with all of these and then do your homework. So that's how we handle distributed loads. It's a little challenging. It's not that hard, but it's got a lot of details that can throw you if you're not carefully paying attention. Good luck.